Good morning. We are going to discuss the second part of Unit 3rd, that is the solution of non-electrolyte. In this, we will discuss some gaseous mixture, then ideal liquid solution obeying Raoult's law, ideal dilute liquid solution obeying Henry's law. We will see the Gibbs-Duhem-Margulis equation and the thermodynamics of the mixing. When the liquids are mixed, what are the thermodynamic properties? Now let us see chemical potential of a component in a gaseous mixture. We have seen that for pure A, chemical potential is mu A is equal to mu 0 A plus RT ln Pa upon P0. P is the pressure. If another substance B is added to it, then the equation is mu is equal to mu 0 A RT ln P upon P0. This is Pa. This is the partial pressure. Now chemical potential in liquid mixture. This is the basis for discussion about chemical equilibrium. So here we have to use chemical potential. Suppose A and B in liquid phase, A and B in gas phase. So chemical potential at equilibrium, both the chemical potential should be equal. Means chemical potential of a gaseous form of a substance A is equal to chemical potential of its condensed phase. Now chemical potential of ideal liquid solutions, that is Raoult's law. In this, we shall make use of the subscript star to denote the chemical potential for a pure substance. We will use this star. It will represent the pure substance like this. If we need to distinguish between liquid phase and a vapor phase, the vapor pressure of a pure liquid is Pa star. The chemical potential of A will be given by these expressions. Suppose another substance is present, then Pa by P0. So by combining this equation, we can reach to this, because Pa upon Pa0 is nothing but the XA mole fraction. So we can get the expression mu A is equal to mu A star plus RT ln XA. Now about the chemical potential of ideal dilute solution, for which we have seen in the last discussion Henry's law. He had found a real solution at low concentration, that is vapor pressure of the solute Pb. It is proportional to Xb. Proportionality constant Kb, that was Henry's constant. So here in this case, this will be the expression for mu A. Now the chemical potential of real liquid solution. Here we have to see the activities. Whenever we are considering the real solutions, we have to deal with the activities. The equation for chemical potential in terms of vapor pressure, this, which holds for both real and ideal. But in terms of mole fraction, it holds for ideal solution only. This obeys Raoult's law. When we replace this X by A, then we can use this expression successfully for real as well as ideal. Otherwise, you will use this expression for ideal solution only by Raoult's law. But if you replace this X by activity, now we can successfully use this expression for both real and ideal solution. Now we will see the Gibbs-Duhem-Margulis equation. Very important equation asked many times in the exam, which has been derived from Gibbs-Duhem only. Some extension of this Gibbs-Duhem equation found out by Margulis, known as Gibbs-Duhem-Margulis equation. This is Gibbs-Duhem equation as we have derived in Unit 1. From this we can say this. Now these are the mathematical steps. Divide by Na plus Nb, we will get like this. Dividing by dxa, we get this. Now replacing xa in terms of xb, we will reach to this. Now chemical potential is given as mu is equal to mu 0 plus RT ln P. So the expression will become like this. This is for mu A. Similarly, we can write down the expression for mu B. and by putting this both the equation in this, we will get this. So finally, separating the term, we reach that d ln Pa upon d ln Xa is equal to d ln Pb upon d ln Xb. This is the Gibbs-Duhem-Margulies equation, which relates partial pressure of two constituents with their corresponding mole fraction. And the main thing is this equation is applicable for both ideal as well as non-ideal liquid mixture. Otherwise, we have taken into consideration activities, but here mole fraction successfully used for the real as well as ideal solution. Two partial pressure related to their respective mole fraction, applicable for both. But the assumption is made that vapor behaved ideally. The Duhem-Margulies equation, it can be used to show that if one component behaves ideally, other must behave ideally. Or if one component shows positive or negative deviation, other will also show the same deviation. We will see. First, we will prove that if component A is behaving ideally, then the component B will also behave ideally. This has been also asked many times in the university exams. Derive Gibbs-Duhem-Margulies equation and prove that if A is behaving ideally, second also behaves ideally. Now for that we have to start from this Raoult's law, and taking the log, derivative and the ratio, we will reach to this one. Now here we will use Gibbs-Duhem-Margulies equation and we will apply the same for B. And again by the reverse calculation we will reach to this expression for B like this. Means start from Raoult's law, reach to Gibbs-Duhem-Margulies. From Gibbs-Duhem-Margulies, start with B and reach to again Raoult's law for B. That means if in binary solution A was obeying Raoult's law, we will reach, using Gibbs-Duhem-Margulies equation, we will reach to the B and shows that B also obeys Raoult's law. That means A is behaving ideally, so B is also behaving ideally. Means if any one of the component is behaving ideally, the other component must behave ideally. Now another, we can see that if a component is showing positive deviation, then the other component will also show positive deviation. For example, again we will see that for A component, PA for real greater than PA for ideal. So ln will be greater, then this will be also greater. Then here we reach to this conclusion, and again using Gibbs-Duhem-Margulies equation we derive the same expression for B, and again by the back calculation we will go to this stage. Here also we can prove that if one component A was showing positive deviation, B will also follow this equation, and we will see that B will also show positive deviation on the similar line. This can also be asked in the exam. The two things which we have observed, if one is behaving ideally, other will also behave ideally, and if one is showing positive deviation, other will also show positive deviation, or we can consider it for negative deviation also, just the matter of sign. So we can prove successfully. Now it's integrated. Now we will see the integrated form of Clapeyron-Clausius equation. We have Clapeyron-Clausius equation dp by dt, which we have studied in unit 2. dp by dt is slope of the pressure temperature curves, which was Q by T, H by T, change in the volume, difference in the volume. So by taking the integration between the limits T1 T2 and P1 P2, we can successfully reach to this equation, that is the integrated form of Clapeyron-Clausius equation. What is the application? Application is, see we have 5 quantities again. We can calculate molar heat of vaporization. We can calculate the effect of temperature on vapor pressure of a liquid, effect of pressure on boiling point, calculation in the molar elevation, molar depression constant, everywhere. Means we have 5 quantities. If 4 are given, we can calculate any 5th quantity, which is not given. So these are the important applications of Clapeyron-Clausius equations. Now, we will see the thermodynamic parameters when the solution is formed, means when we are mixing. When the solid, liquid or gases, they are combined, they are mixed, the thermodynamic quantities, they experience a change as a result of mixing. So we will see the mixing which effect on the Gibbs energy, enthalpy, entropy and volume when we mix two things. A solution is created when two or more components mix homogeneously to form a single phase. The solution of this study, the study of these solutions are very much important in chemical engineering programs. Now, understanding the thermodynamic behavior, it is an integral part of the study, either ideal or non-ideal, because it provides valuable information on the molecular properties of the system. Most real gases, they behave like ideal gases at standard temperature pressure. This allows us to combine our knowledge of ideal system and solution with the standard set of thermodynamics to reach to the set of equation which can be useful there. So we will see when we mix the solutions, whatever may be the changes in the thermodynamic parameters of G, H, S, V. So this is Gibbs free energy of mixing. Unlike any extensive property which rely on the amount of the substance, the extensive property of a solution depend on its temperature, pressure, composition. This means that mixture must be described in terms of partial molar quantities. The total Gibbs free energy of a two component system is partial molar property 1 plus partial molar property 2 with the number of mole fraction of the component, number of moles of the component should be taken into consideration. Just like we have seen in the first unit, V is not equal to V1 plus V2, it will be N1 V1 plus N2 V2 like this, where G is total Gibbs free energy, N1 N2 number of moles, G1 bar, G1, G2 bar are the partial molar free energy, which we call is chemical potential. The molar Gibbs free energy is this, where G0 is it is a standard molar Gibbs free energy of 1 bar. P is the pressure. Now, in a mixture of ideal gases, we know that this is equal to chemical potential. This means that the equation can be written like this: Gi bar means mu I, that is equal to mu I0 plus RT ln this. Now, we have two gases at same temperature 1 and 2, so Gibbs free energy can be mixed. We have to see that what is the Gibbs free energy initially, and finally we will see its difference to find out the Gibbs free energy of mixing. So initially, if it is a two component system, then this will be N1 mu1 0 plus RT ln P, N2 mu2 0 plus RT ln P. When they are mixed together, then the Gibbs free energy finally should be equal to N1 mu1 0 plus RT ln P1, and this will be P2 because they will exert a partial pressure, P1 P2. This P1 P2 will be equal to total pressure P. So we have to replace finally when they are mixed P by P1 and P2, partial pressure exerted. So when they are mixed, we know that P is equal to P1 plus P2. This means that final Gibbs free energy mixing will be equal to this, final minus initial. So this expression minus this expression. What is this? P1 upon P? Raoult's law, X1. This is X2. So that means we can reach to this expression for this is two component system, but for more generalized way we can use RT, summation of Xi ln Xi. This Xi ln Xi delta mix of G, that is Gibbs free energy of mixing. Here molar, because we are divided by n. If you don't divide, no problem. you can use delta mix of G is equal to nRT. Or you can use delta G of mixing per mole. Only you have to take care of the units. Now entropy of mixing, we know entropy is del G by del T. So simply we have the equation for delta G of mixing. We will find its differentiation with respect to T. So the term T will go and the remaining will be our entropy of mixing. It will be minus. And only just we have to divide this expression by T and change the sign. So if in an exam problem is asked, just find out one quantity. For entropy, just divide it by temperature and change the sign. You will get entropy of mixing. So when the two gases mix, then the two gases expand, then the entropy of mixing is given by this expression. Since the mole fraction again lead to the negative values in x1 and x2, negative sign, it makes delta mixing positive. So mixing is a spontaneous process. This mixing is a spontaneous process because mole fraction ln x1, x2. ln of x1, x2 give negative value. This negative become positive and the makes delta mixing positive. So entropy is positive. That means it is a spontaneous process. Now enthalpy of mixing. We will see the enthalpy of mixing. We have just find out the entropy of mixing, Gibbs free energy of mixing. We can put the values successfully here and we can find out delta H. When we put the values here, we came to conclusion that delta H of mixing is 0. It is 0. That means the molecule of ideal gas spread out enough that they do not interact with one another when mixed. No heat is evolved or produced. As well as there is no change in the volume. This we have discussed in the first unit also. Whenever we are mixing the ideally, then there will be no change in the volume and the enthalpy. So suppose this is 0, this is mole fraction, we are mixing. So delta X going to positive, Gibbs free energy going to negative, and delta H here, this term can be written. So delta H and delta V remains constant 0, no change, 0. So in the examination, if the numerical has been asked, problems can be asked to find out all 4 quantities. Just find out the value of delta G, divide it by temperature, change the sign delta S and write down directly delta H and delta V as 0. The problem can be of 2 marks. 2 marks for this and this. You just have to calculate one and you can find out the another property and you can simply write down delta H and delta V as 0 and 0. Just take care of the proper units. So likewise, in the exam, you are able to solve the problems also on this unit.